Alright, so what causes simple harmonic motion? So we've looked at a mass on a spring vertically. Let's look at one horizontally on a frictionless surface. So again, we're looking at kind of an ideal situation. So if it's frictionless, mu equals 0. Alright, so here's our initial point where it's compressed, and then we'll have an equilibrium point. We'll call that stretch 0, and then where it's going to go on the other side. So our two positions will be negative x and x. So if I have the spring compressed, let's look at the forces acting on it. So the free body diagram, all right, we're going to ignore all the vertical forces. The spring force is pulling to the right, towards equilibrium. When it's all the way extended out to the right at positive x, the spring force is going to be pulling to the left. And when it's at equilibrium, the net force is 0. There is no spring force acting on the block at that point. So you'll notice that at all of these points, the spring force is always pointing towards the center. All right, last week we did pendulums. So let's draw a pendulum. Okay, and then we're going to put a dashed line for the two maximum amplitudes that we have. So when we do that, we'll have some maximum initial amplitude of theta. There we go. So, and then again, let's do free body diagrams for each of these points. So this one gets a little more complicated. So we have gravitational force down and some tensional force along the string. At the bottom, we have gravity straight down and tension straight up. And then on the right, it's a mirror image of the one on the left. So let's put those labels in. So tension for all of the ones at the top, and then gravity straight down for all of them. But this is a little more complicated, so we have to look at the net force, right, that's acting at each of these points. So if you look at the net force, at the bottom, the net force is 0. At that moment, it's at equilibrium. If I didn't displace it, it would never go anywhere. So on the left, the net force there, all right, is actually down and to the right, towards equilibrium. And on the right, the net force is down and to the left. So again, we see that the net force always points towards the equilibrium point. So that's kind of interesting. And you could do this for any set of points. And we're going to go back and we're going to look at the spring. And again, the net force always points towards equilibrium. So what we call this is a restoring force. All right, so ultimately, what causes simple harmonic motion is when there's a restoring force that wants to restore the object or the system back towards its equilibrium point. However, when it gets to that equilibrium point, it still has velocity, so its momentum is what carries it through and on towards that next maximum displacement.